Okay, so we are now live and I'm starting the
Okay.
just 1 or 2 minutes and then you can welcome
Yes,
the
sure.
participants, and we start at PM. Sure.
So now people are actually watching us like, hey.
My students are here.
You can see name.
You can start.
All right, thank you so much for coming this beautiful webinar called Recent Technologies and Structures on Seismic Response Control in Japan and Philippines. So we have like all the moderators and speakers here. And this is actually very first time to collaborate with two different national teams like Japan and Philippines. So thank you so much for taking your time. And let me share my PowerPoint screen here. So very quickly. So this is the joint webinar. And today's program, actually, we have about 120 minutes. Now we are in the opening session and we have three beautiful speakers, Professor Takeuchi and Dr. Rodolfo and Professor Nagayama. And we may have a question and answers closing time. All right, before we start the webinar, let me thanks to the sponsors. We have two sponsors, Alpha Tech and Kawaking, and give me a 2 minutes about the 2 minutes about the sponsor videos now. Sorry.
音が出てないよ。
There's no
Our
sound.
Cortec is renowned for wide-ranging excellence in engineering. Our seismic isolation bearings and vibration control dampers play a vital role in all manner of buildings and bridges. And by leading the way in casting and processing technologies, we've forged a history of more than 60 years. Today, you'll find our products at work everywhere, fueling pride in local landmarks and ensuring peace of mind throughout Japan and overseas. Today, Awakin Cortec continues to serve the needs of changing times, developing ever more sophisticated technologies that bolster our reputation, such as seismic isolators for bridges and for buildings. By applying our advances, we also reinforce existing structures around the world, providing value-added solutions that equip achievements of the past with the strength to withstand the future. Because our advanced damper-based vibration control system is universally adaptable, cost-efficient, and easy to maintain, it's an extremely popular choice for installation in new and old buildings alike, and in public facilities such as schools and hospitals. Superior reliability of Kawakin Cortec product is underscored by rigorous testing. We employ material with real-world proportions to analyze seismic and other effects, and we apply our findings to the development of new products. We use the largest testing machines in Japan to guarantee the highest levels of product performance.
Thank you so much. And so today's webinar, before we start the webinars, let me introduce this YABSE organization. Some of you are already members, but some of us are not very much. So YABSE is International Association for Bridge and Structural Engineering. To exchange knowledge and advanced technologies, advanced to practice of the structural engineering worldwide. So YABSE is actually very old one. So the YABSE is scientific combining members in 100 plus countries and counting 60 plus national groups worldwide, and founded in 1929, set in Zurich. So YABSE is dealing with the aspect of the structural engineering contains everything. The president of the YABSE is now Harsher. So the YABSE objective is actually the following objective: to promote the cooperation and understanding among all those concerned, to encourage the awareness of the responsibility of structural engineering, to encourage actions necessary for the progress, and to improve and foster cooperation and understanding between organizations having similar objectives. To do so, we have this annual meeting, we have our committee members, and also we have this congress and the seminars and conferences twice a year, every year. And next one is coming for the Incheon. So Incheon early bird will close until 19th of July. So please join it. And also the next one is Guwahati in next year, 2027, about April. So this abstract will be closed 15th of July. It's still open. So please also submit it for this conference. And also we have the publications, the Structural Engineering International Journals. And also we have this like national groups. Now we are now like Japan and the Philippine groups. And this is also the technical activities. So if you're interested in one of them, you can always join it. And if you're young engineers, like students, you can also join these young engineering programs. So then now let me pass to the Professor Nakamura introduce about the National Group of Japan.
Hello, I'm Shunichi Nakamura, a core member of the Japanese group and a former vice president of ABSE. I'd like to give a short introduction to the Japanese group. I must begin with some sad news. The chair of the Japanese group, Professor Yozo Fujino, passed away on June the 6th. He was a great leader, and his contribution to YABSE was truly remarkable. Please join me in observing 10 seconds of silence in honor of his memory. Begin. Thank you. We, the Japanese group, have continuously contributed to the activities of YABSE in many ways. We have hosted several YABSE symposia, and our members have actively served on the various YABSE committees. In particular, we successfully organized the YABSE Symposium in Tokyo last year, which welcomed nearly 600 participants from 45 countries. It was one of the largest and most successful YABSE conferences I ever held. We initiated the YABSE Young Engineers Colloquium East Asia with the national groups of China, Korea, and Hong Kong in 2018. 5 events have been held so far, they were all very successful. The YEC last year was special, being a joint event organized by the East Asian and German national groups. We, the Japanese group, will continue to contribute actively to YAVSE activities in the years ahead. And we sincerely appreciate your continued support and cooperation. Thank you very much.
Thank you very much. And now, please introduce the National Group of Philippines, Professor Andres, please.
Okay, thank you very much. I'm Dr. Adi Oreta. Actually, I'm the outgoing chair of the Philippine Group of YABSE and passing it to Dr. Rodolfo Mendoza. So let me introduce YABSE Philippines Group. Basically, the mission is to promote global networking among civil and structural engineers and to advance the knowledge and expertise and practice of Filipino civil and structural engineers through continuing education lectures, seminars, and conferences. No? To achieve this mission, the group was formally founded in 2014, and presently now, Dr. Mendoza will be the chair of the Philippine group. Among the activities organized by the Philippine group of YAPSE will be shown in the following slides. We have participated in several YAPSE conferences, starting with Bangkok in 2009, Korea 2012, Spain 2014, Japan in 2015, Guangzhou 2016, Stockholm, Malaysia, New York, Prague, and recently in Tokyo 2020. We also organize a CPD lectures as shown here, lectures on earthquake anti-seismic devices. We also have lectures or forum promoting outstanding structures that are recognized by the YAPSE, specifically during its 90th year. And this is a group photo of that particular forum, which was actually featured in the New York meeting. We also organize webinars, and this is an example of the webinars we organize, starting from introducing structural engineering and outstanding bridges, outstanding buildings, and updates on the Philippine National Structural Code of the Philippines. Other webinars include topics on innovative and sustainable construction materials, where our speakers were presenters in the YAPSE symposium in Prague. And we also conducted more webinars, specifically targeting our Filipino engineers, civil and structural engineers, from the basic structural analysis design to application of artificial neural networks, application of drones in our practice. And we have here, unfortunately, Yuzo Kojino was one of our invited speakers here in the Philippines, and I'm so sad about the news. And we also invited other civil engineers and representatives from YAPSE from other countries, as shown here. So, other conferences, we are cooperating with the Association of Structural Engineers of the Philippines, which is the main organization focusing on structural engineering. And this is now the present group of YAPSE, consisting of coordinating council members, about 10 members. So if you want to know more about the Philippine group of YAPSE, you can visit the following site, where you can read updates about YAPSE Philippines and watch the webinars which I presented earlier. Thank you very much for your attention.
Thank you very much. All right, let me start the webinar now. Okay. So this webinar is actually the concept of the containing of the structure monitoring, model validation, damage sensitivity, and post-earthquake support and resilience-oriented designs. So it's gonna be broad, wide topics here. And today, because it's in collaboration with two national groups, the first speaker is Professor Toru Takeuchi at the Institution of Science, Tokyo, Japan. And second speaker is Dr. Rodolfo Mendoza at the La Salle University and Petrojikin. And finally, we have Professor Tomonori Nagayama at the University of Tokyo, and he is also the Vice President of YABSE. So during the webinar, you have the Q&A corners, like you can see some extra button at the bottom. You can click more or something, and you can see questions and answers here. And then you can type any questions during the speakers are speaking. And we're gonna have a 10 or 15 minutes question and answer time, and then speakers will try to answer all your questions. But if we don't have enough time, we will send you back in following days. All right. If you don't have any questions, we will start the webinars. Professor Takeuchi, if you're ready, you can start anytime.
Okay. Thank you very much.
Thank you so much.
よいしょ。Can you see my screen now?
Yes.
Okay. Thank you very much for introduction. I'm Toru Takeuchi from Japan. I'm a professor emeritus of Institute of Science Tokyo, previously at Tokyo Institute of Technology. I'd like to talk about the recent borderless design between seismic isolation and response controlled building structures in Japan. So as you know, Japan is a very high disaster country. And we have a big earthquake and the typhoon and the flood and also the volcano. So we have some, my back have the picture of the Noto Prefecture earthquake in 2024. And also we have many earthquakes in all over the world. Recently also we had a big earthquake in South America, I think. So because of this kind of disaster, now the seismic isolation and response controlled structures with the energy dissipating devices or dampers have been widely applied to large numbers of the buildings in all over in Japan in these 30 years. And they have been recognized as one of the ordinary structure options. As a
Professor
result,
Takeuchi, Professor Takeuchi, can you
Yes.
check can you check the size of the slide?
okay, too big? You can't see the full size?
We can't see the whole slide.
Okay. Probably another one could be
That's fine. That's fine.
okay. Okay.
This
Yeah.
is fine.
Yeah, okay, thanks. Yeah. So there is a many the system is other is now the developed on the boundary between these system, and so between the seismic isolation and response controlled buildings, their border is becoming ambiguous. Seismic isolation and response controlled structures share a common concept of. Okay, so probably this one is should be erased, I think. Oops. How to okay. Oops. Oops. Yeah, okay. So the seismic isolation and the response control structure share a common concept of firstly designing the main structure to support the self-weight in elastic and soft in that means the increasing natural period. And the second is reducing response by the energy dissipation devices like dampers or fuses to absorb the seismic energy. So recently realized the system in Japan's categorized in these figures. So upper one, okay. Oops. Oh. Okay, so this one is in the upper row indicates the mid-level seismic isolators, while the right side of the upper row, this one is the structure is supported by long clamps instead of seismic isolation bearings. As similar, the mid row is indicate a combined system including both systems. The lower row, this row has the indicating grid skin structures and the spine structures with seismic isolation and spine structures with seismic isolation and response to controlled concept. In the following, detailed application example are discussed with their characteristic. So firstly, this is example of a mid-level seismic isolation system. These are increasingly being applied, especially in the very Tokyo central area, to avoid the loss of site use near the property boundary at the ground level and the risk of flooding. There are two types. These in which the lower floors are designed to be rigid, like this, like left side in the Teco buildings, and designed as a soft with viscous dampers as the Roppongi Tri 7 in the right. And in principle, vibration control system with a soft first story is similar to the seismic isolation, where the deformation is concentrated in the lower layers. This Nippon the TV Bancho Studio introduces a soft lower story and with viscous dampers on the top of the diagonals, and that is obtained the seismic isolation effect without using a seismic isolation bearings. Although such a system need for integrity at the deformation concentrated layers, seismic isolation pits are no longer necessary. However, in such seismic isolation using a long clamps, consideration must be given to avoid the excessive damage concentration by the P delta effect. So only limiting first story in the very small height is not recommended. To distribute it at least 2 or 3 stories is more suggested. And this figure shows the example of the structure that combines the seismic isolation and the response controls together. This in Roppongi Grand Tower in the left. Damping devices are also distributed in the lower structure. Isolated layer is here, and upper part is isolated to the buildings, but the lower part is energy spacing device distributed. So combined with response control structure and the seismic isolated structure. In right side, this is a Yoyogi seminar tower. It's combined with coupled wall structures, and the whole structure is supported by the seismic isolated bearings with the actively controlled oil damper, and also they have producing the shear deformation at the between the two coupled shear walls, and distributing the viscoelastic damping devices to reducing the seismic and the wind vibration effect. And this is a combination of the outer braced framed structure around the perimeter that is called as a diagrid or grid skin combined with a seismic isolation system. The outer grid skin structure is with the diagonals with this is increasing the horizontal stiffness of the superstructure. So that is a good match for the seismic isolation system. One of the early example is Sony City, that the isolated layer is a ground level, But recently completed the Daigate Ikebukuro have the seismic isolated layer at the mid level, and this supporting structure is to allowing the train to go through under the supporting structure. And also this diagonal is designed very elegantly lightweight. So this lightweight appearance is achieved by separating vertical support of the clamp is also provided for the internal spaces, and the diagonal members in the outer skin and were released from the vertical bearing load. So diagonal, the braces is only taking care for the stiffness for the horizontal force. That makes structure looks very elegant. So in the mid level, you can see the rubber bearing support and also the steel dampers in between. So this figure is example with spine in the center. That is a concrete core. In this kind of the concrete core system with a sliding form is very common in all over the world in the outside of Japan. But in Japan, it's not so popular because of the unstable collapse mechanisms and the deformation performance under the severe earthquake. So, but this problem is can be resolved by the seismic isolation. This Toda new headquarters is the one of the tallest seismic isolated office buildings. It reached 165 meters height, and all the concrete core can have a stiffness for the whole buildings, and also whole thing, the weight is supported by the seismic isolators. So because of the weight of the buildings, laminated rubber bearing about 2-meter diameter, that is one of the biggest one, is upright, and also semi-active oil damper and oil damper with a trigger is distributed for the control the acceleration. So because of the high stiffness of the core, the walls, their performance under the severe earthquake, it 100 to 500 years return period is kept under 200 gals, which satisfies the continuous operation even under the severe earthquake. And another structure system with the core spine frame with a rocking and energy station members are also called as controlled locking frame or damped spine system, or sometimes a strong back system, and has been applied to the seismic retrofit of old steel buildings in US. In Japan, there's a retrofit of G3 buildings. That is all the frames is attached to the new the spine wall with a pin supported with the damping devices on the shear place was used for the to controlling to the collapse mechanism and avoiding the damage concentration at the typical floors. And this concept is also used for the new building of material research building in Science Tokyo in this Yokohama campus. And I introduced locking elastic steel the spine truss frame, and this locks and the dissipating energy at the vertical dampers, buckling restraint clamps, and that can be controlled all the shear drift in the evenly and avoiding damage concentration. So that is applied to the new buildings. So, or damped diagrid, which introduce energy spacing device into diagrid member, also have wide varieties. One of the early example, the Sankyo building in Shibuya, it looks like a fully diagonal, but part of these diagonals the buckling restraint brace is the dampers and have energy to avoiding buckling for the elastic members. And recently, another example is right side, the Tokyo Torch Tower now is under construction, and with about 400-meter height in one of the highest buildings in Japan, introducing a slit in the perimeter grid skin to amplify the vertical shear deformation, and has energy dissipation devices distributed in this slit. So similar as multi-story structures, application of the seismic isolation and response control system are getting further popularity for the spatial structures, indoor stadium and arenas. For example, in Japan, Osaka Suita Stadium on the left, and the Tokyo Aquatic Center in the right, and the Ariake Arena for Tokyo Olympic 2020 employed a seismic isolated system for the roof structures. So for the supporting a roof, they have a isolated roof layer like this. And on the other hand, National Stadium of the Japan employed the energy dissipation system for the lower 3 layers of the supporting structure, and that is a similar concept as Nippon TV Bancho Studio. So that is kind of the quasi-seismic isolated types. And back to here is a detailed introduction to the Tokyo Torch Tower mentioned earlier. This building is currently under construction, but once completed, it will stand with 385 meters tall, making it the tallest building in Japan. With an extremely large floor plan, this one line is 100 meter by 100 meter. It was determined that damped outrigger was tried, but it was not functionally effectively. So therefore, the plan is to adopt it to a braced tube structure to control the natural period to keep under the 7 seconds, and also incorporating the vertical the slit into the tube to amplify the shear deformation, and insert the dampers to these slit to ensure the high damping. Okay, so this is a plan and the elevation of the buildings. The left figure shows the structure plan view, and it has a big plan of the 100 meter by 100 meter. At the corner and the center of each part, in the 8 places of the plan, they have a slit. And in the slit, in the 4 layers or 3 layers of the oil dampers were distributed. In each part, they have the large number of the oil damping devices is distributed. So these oil dampers enable the damping ratio to reach to 10% or higher for the whole structure system. So this table shows the design criteria. The response has been evaluated for near-field earthquake and the long-period ground motion based on far-distance earthquake, considering the Nankai Trough earthquake, and is limited to a response that allows for the continuous use even after such kind of earthquake, with the interstory drift as 0.4%, 1 by 250 radian for the design earthquake. And for the maximum considered earthquake, still under the 1 by 150, that is 0.467%. So that is no harm for the interior or curtain walls. So here is a construction of status as June of this year. Last month, you can see the massive diagrid is constructed in the lower part, and also in the slit you have seen oil damper of the big 4,000 kilonewton capacity damper. 4 numbers of those, and 8 numbers of 2,000 kilonewton is to upper was bundled together, and also you can see how massive the building is comparing from the other buildings. It's a 100 meter by 100 meter. Probably it's reached to probably go over 4 times of this length. Okay, so the later part of my talk, I talk about the recently completed seismic isolation bearings testing facilities called e-isolation. That is to working many the people together with not only these ones, so many people. So please check these web pages. So explained about the trend toward large-scale seismic isolation and vibration control structure is gaining popularity in the world. To address this trend, a large scale of the dynamic seismic isolation testing facilities completed in the US, Taiwan, Italy, and China. And 2 years ago, so we completed e-isolation in Japan. So in these facilities, test specimen is compressed by applying a high vertical load from the bottom and received by the reaction beams through the moving platen. So here the specimen was compressed in a very high axial load. And also the moving, this horizontal dynamic jack is moving the platen in the horizontal way. And the reaction forces of the specimen was measured by this load cell. But the problem is here have a bearing with a very smooth size, but there's still the very high compressed load. Still there have some friction is introduced. And also the moving platen is to shaking in dynamically. Their inertia force is also introduced into the load cell. This load cell is measuring specimen's shear force, but also the friction forces and the inertia force can be contaminated into this load cell. So this is a common problem that this friction force and the inertia force have some testing times, some reach to 20% or something. So this is very difficult to remove it in the models. So then new seismic isolation test facilities in Japan, we are changing the concept. Reaction beam is not fixed, supported by the horizontally soft the bearings, that is a rubber bearing, and then connected rigidly to the reaction force measurement link, and the load cell was placed here. So that means when moving here, actual the friction force is not moved to here, and also the inertial force is not affected on here because reaction beam doesn't move up too much. So this load cell the forces can correctly the shear force of the test specimen without contamination of the friction forces or inertia forces. So then in this concept, this e-isolation new facility is completed in 2023 in Miki City in Hyogo Prefecture. That is Japanese largest experimental facilities for the seismic isolation and the vibration control system, capable of withstanding vertical loads of 30,000 kilonewtons, horizontal loads of 5,100 kilonewtons, and amplitude of the 1.3 meter under the 800 millimeter sec velocity. So the place of the facilities is placed in the near the e-isolation. E-isolation here in the e-defense, near the e-defense. It's north of the Kobe city in Kobe, and that is in the Miki city. So the reason for the placing here is in the future we can use hydraulic pump of the huge e-defense facilities can be also be expected to use for the reinforcing this e-isolation system. Okay. So this is a scene of the reaction beam is here, and two of the 4 meganewtons rotor cells are linked, and 1.5 meganewtons are two types of the rotor cell, or the rotational constraint link is measuring 99% of the reaction forces. The only less than 1% is to distributed supporting the rubber bearing, but that can be measured by the deformation of the bearing forces, bearings. So we can completely to have a clear direct reaction forces without contamination of the friction of or the inertial forces. So that means by obtaining accurate reaction forces in real time, it is possible to perform a real-time hybrid simulation of any buildings using actual test specimens. In this figure, the green line represents the response values obtained using actuated rotor cell. That is means big reaction forces, the friction forces is the contaminated to the reaction forces. So the response of the building is completely different from the analytical result, that is a black one. So we are using the test of the real specimen, and their reaction forces are going to the shaking model or in the computer, and then a reaction, the deformation displacement is go back to the test machine, and then obtain the reaction forces again, go to the analytical or the models. That is a kind of the hybrid simulation testing machine. So if this kind of the error was occurred, the reaction force response the history itself is can be fatally the fatal error have introduced. In the red one is to obtain the hybrid simulation with a proposed measurement link. They have a very clear linear lines, and their response is very precisely to reproduce pure analysis with a linear model. So this measurement system is quite important for the real-time hybrid simulation. So here is a scene of the how the it moves. It's a lower moving platen is vertically moved, supported by 24 numbers of the vertical actuator, and the upper the moving platen is horizontally moves with 4 actuators, and the measurement ring is supporting the reaction beams. Here is a specimen. Okay. Okay, that is a 1.2 meter diameter natural rubber bearing compressed by 70,000 kilonewtons. Frequency is 4 second, and the amplitude is 400 millimeter. The same specimen can be looked from the side. It's like this. Next one is a friction pendulum. Friction pendulum have the moving up in the horizontal the movement. So in the testing, it's a lower platen should be going down along to the horizontal displacement. But keeping the actual force and moving to go down is a very high the techniques for the control. This facility looks very nicely designed and compact, and the operation room is in right side is designed in the wooden interior. It looks like a living room. So when you visit these facilities, you can stay in very comfortably for the testing scenes. So if you have the time and the budget for the testing in these facilities, please to inform us for your seismic isolated or response controlled structures project. Please to check on the specimens can be tested in e-isolation and join us in the Miki City. Okay, that's my talk. Thank you very much for the kind attention.
Thank you so much, Professor Takeuchi, for your time and great presentation. And please, audience, you can also send us more questions. Thank you so much. So now we move on to the second speaker, Dr. Rodolfo. When you're ready, that's all yours.
Okay, good morning, good afternoon, and good evening to all our participants around the world. My presentation is about the evolution of the seismic bridge design practice in the Philippines, from Spanish colonial era to our goal for resilience-based design through the use of seismic isolation. My presentation outline for today, I would like to start with the history of bridge practice in the Philippines, followed by our evolution from force-based design approaches to the current performance-based approaches, and our goal to achieve resilience-based design through the use of seismic isolation system. The seismic design practice for bridges is not old, and it is actually relatively new, and it started around 1925 after the Kanto earthquake. So if you look at it, that is just roughly 100 years from where we are right now. That is just similar age of one of our prominent late senator in the Philippines who achieved 100 years old before his unfortunate demise in 2025. So we can say that the seismic design practice for bridges is roughly the same age also as the birth of IABSE in 1929. And all of this is because of the event in Japan during the great 1923 Kanto earthquake. If you look at it, many of other great achievements both in sciences and engineering has already achieved centuries before the introduction of seismic design in both buildings and bridges. The birth of calculus and the introduction of elasticity happened in 17th century, and the construction of Eiffel Tower happened in around 1889. In the Philippines, one of the notable structures, which is the San Sebastian Basilica, which was completed in 1891, almost the same time as the Eiffel Tower, was years before the introduction of seismic design. There is a common myth that a story that tells that San Sebastian Basilica was also designed by Gustav Eiffel because they were constructed at the same time. But as an engineer who was involved in the restoration of the church, there is no actual evidence that it was actually Eiffel Tower who designed the system. However, due to the commonality in terms of the steel technology, connection design, and the material use, which both came from Belgium, it is understandable to say that this San Sebastian Basilica was designed by Gustav Eiffel. It was not until the 1908 Messina earthquake that the concept of considering ground motion in the design of buildings was considered, but not until 1915, where we have a formal definition on how we consider ground motions in the design of buildings after Professor Sano of the University of Tokyo introduced the concept of seismic coefficient. And not until the 1923 Great Kanto earthquake that the concept was introduced in building codes in 1924 and in bridges in 1925. In the Philippines, the first bridge ever constructed is actually the Puente Grande de España Bridge, built between 1929 to 1629 to 1630. The bridge consists of a 10-span, which connects the Intramuros and now what we call the Arroceros area. The structure is originally made of a superstructure timber, and the substructure is made of a massive granite stone piers. The bridge is said to survive the 1645 earthquake and 1663 earthquake, but was totally damaged during the 1863 earthquake, which was then replaced by the Puente de España Bridge in 1875. This Puente de España Bridge is a 6-span stone masonry bridge following the Spanish bridges, which consists also of 2 central arches made of iron. The iron is said to be manufactured in France by a French company, Imbert and Company, and directly shipped to the Philippines. The bridge survived until its subsequent replacement in 1920, where it was replaced under the American colonial era and named it as Jones Bridge. The Jones Bridge, as we know it, was designed by one of the first pensionados, or these are engineers or architects from the Philippines who were sent in the US to study engineering and architecture. Juan Arellano, of course, is one of those people who were sent to Drexel University. It was also during this time that many roads, bridges were upgraded, including the famous Gabaldon School buildings, through the American colonization of the Philippines. But even up to this time, there was no account for seismic design or earthquake provision in the design of this building. 1961 was the year where the Association of Structural Engineers of the Philippines was established, and from there on, the consideration for seismic forces has been considered. In 1982, DPWH requires the design of bridges to consider at least 10% of the gravity. This was followed by the provision or the release of the ASEP NSCP, or the National Structural Code of the Philippines, Volume 2, which is actually dedicated for bridges in 1987. After the 1990 Luzon earthquake, DPWH produced or released a department order which requires all bridges to conform to the latest AASHTO provisions, and later on these provisions were adopted by ASEP under its Volume 1 in 1997. From there on, the DPWH, together with the support of JICA, produced new standards, and the penultimate is the 2015 release of the DPWH DGCS, which updates all the guidelines for bridges, including standards for seismic provisions following the LRFD bridge seismic provisions, and also the introductions of seismic isolation guidelines. If you look at it, the development of code in the Philippines transitioned from the original force-based design concept into its transition to capacity and displacement-based design approaches. And now we are looking at how we can further improve our bridge design practice from this capacity-based design and performance-based design to full resilience-based design approaches. In the force-based design in the Philippines, the design of the bridges identified substructure as the main earthquake-resisting system for design, and a single ductility factor is actually used in order to represent the ductility of the entire system. This concept is the same concept that has been applied in the US for buildings and was also adopted for bridges in the Philippines. Clearly, there are some limitations with this approach, and this resulted in some of the damages during the 1990 Luzon earthquake, which includes damage to foundation, soil liquefaction, the unseating of superstructure, pier collapse, and deformation due to lack of ductility and insufficient seat width. However, through the introduction of the new standards, following these learnings from the earthquakes, we have now adopted a combination of code following both the US standards and the Japanese standards. The new DPWH standard for bridges has adopted both the AASHTO provisions and the provisions for Japan Road Association in the design of bridge. Specifically, this provision still adopts the definition of R value as a one system ductility factor for representing the substructure selected for a system, but this time we are now introducing two levels of assessment for our hazard levels. We have also adopted seismic performance requirement, which are mostly patterned from Japan Road Association guidelines. And we have introduced also seismic verification, although mostly on force-based design approaches. The guideline has also introduced and defined a specific earthquake resisting system. And now, for the first time in the code development for bridges in the Philippines, we have introduced the use of seismic isolation as one of the earthquake resisting systems to control the response of bridges both in longitudinal and transverse direction. Specifically, in the current BSDS manual of the DPWH, there is a particular sections that discuss solely about the design of seismically isolated bridges. Now, to further encourage the engineers on the use of seismic isolation to bridges, a highway bridge seismic design manual and specification was further introduced. This now allows us to use the seismic isolation layer as the primary system in absorbing earthquake demand, while we still allow secondary plastic behavior in piers and abutments. In this method, the fuse or the main system that is used to absorb earthquake are now the isolation layer, which allows it to absorb the demand forces from earthquake, and at the same time, it lengthens the period of the bridge, which further then minimizes the seismic demand on the substructure. So if we look at the original and approaches in the Philippines and compare it with the current approach, using the ADRS, or acceleration displacement curve, given a demand, conventionally, we design the substructure for bridges in the Philippines as a very, very massive system in order to have a capacity higher than demand. Through the introduction of the capacity-based approaches, we introduced the concept of ductility and capacity-based design, where we can now design flexible and highly ductile structure. But with the introduction of the seismic isolation system, we can introduce the seismic isolation to reduce the demand on bridges by incorporating lead rubber bearing or lead rubber bearing as well as dampers in the structure, which reduces the demand on the structure by increasing the damping in the structure and increasing the period of the structure, which then ensures that there will be no damage on the substructures even after a major earthquake. Of course, there are some limitations in the use of the seismic isolations in the Philippines, which are highly listed in the DPWH BSDS guideline. For example, we are not allowed to use it on subsoil condition unless proven otherwise. If the bridge has a very long period, if there is tension in the support reactions, and currently our DPWH guidelines only supports lead rubber bearing with plug and also high damping laminated bearing. Currently, the use of friction pendulum system is not covered by our guidelines. To show you some application of the isolation system in the Philippines, one of the projects we were involved with is the construction of the proposed Panshan Viaduct. This Panshan Viaduct consists of three bridges we call the Panshan Viaduct: Panshan Bridge 1, Panshan Bridge 2, and Panshan Bridge 3. The Panshan Viaduct is a project that connects the existing Patapat Viaduct along the Manila North Road in Ilocos Norte. Panshan Bridge 1 consists of a total of 496-meter length, while Panshan Bridge 2 is a simply supported bridge with around 26.5 meters in length, and Panshan Bridge 3 has a total length of around 1.2 kilometers. Panshan Bridge 1 has a total of 11 45-meter span. The superstructure is made up of pre-stressed concrete deck girders supported by single rectangular piers. The foundation sits on 6 2-meter diameter board piles, and the superstructure consists of 7 AASHTO Type 6 modified girders. Each of these girders is supported by high damping rubber bearing with lead plug. Some of the details of the superstructure, substructure, as well as the material properties adopted for this specific bridge are shown in this slide. The Panshan Bridge 3 is a 1.2 kilometer viaduct, which consists of a total of 28 spans. Again, each span is typical, around 45 meters in length, and the structures follows the same configuration as Panshan Bridge 1, including the geometry of the girders as well as the coping beams. The geometry and details of this bridge are again shown in this slide. For these bridges, a site-specific seismic hazard assessment was conducted for the entire project to produce 2 levels of design earthquake. The PGA and spectral parameters, as shown in this slide, are provided for level 1 earthquake and level 2 earthquake. Level 1 is a 100-year earthquake, and level 2 earthquake is a 1,000-year earthquake. Now, due to the proximity of this bridge to an existing fault, we were able to produce two types of level 2 earthquake, one that is normal to the fault and one that is parallel to the fault. Using the generated spectra, we have extracted ground motion data from Pier NGA West 2, and utilizing this, we match those spectra from the site-specific record in order to generate ground motion records for nonlinear response history analysis. Now, in the Philippines, under BSDS, you can carry out at least 3 ground motion records and take the maximum response from these 3 records as the basis of performance, or get the average of 7 ground motion records in each direction and use the mean value to actually evaluate the performance of the structure. In the design of seismic isolation, we normally follow this approach when we design isolator system. And in most cases, we already work with the supplier of the seismic isolation before we even start the project. So basically, from the bridge design and bridge information, we develop the geometry, initial sizing of the elements, as well as the initial configuration of the bridge superstructure, as well as substructure and foundation. From this, we develop the mathematical model to represent a 3D configuration of the structure, and we collect or extract the vertical reactions from the support conditions. Using these vertical reactions, we provide this information to the supplier of isolators, which then size and provide the parameters, including mechanical properties of isolators, which we will then use as input to our mathematical model. So this is an iterative approach, and we commonly exchanges data until we achieve the target performance for the bridge. This slide here shows you the assignment of the high damping rubber bearings on both Panshan 1 and Panshan 3 at expansion joint as well as continuous joint locations. This slide shows you some sample input parameters that the seismic isolator manufacturer is providing from the given input vertical loads. Here, the input parameters were provided by Kawakin and Alpatec, which are the local supplier here in the Philippines. Now, these parameters were used to model the bilinear response of the isolators, and the models represent some of the key mechanical properties of the isolation system, including the stiffness, the strength, the energy dissipation, and this process of modeling was iterative, and we refine until the target bridge performance is actually achieved. Using these parameters from the supplier, we then input these parameters to our chosen software and mathematical model in order to confirm if the performance of the system matched the target performance. Here, showing you a geometrically correct model for all the bridge that we considered in this project. The superstructure, together with the girders, were actually modeled geometrically correct, and the isolators were placed under each girder. The isolators were modeled as link elements, nonlinear link elements, and including the substructure as well as the piles supporting the foundation. For this viaduct, the bridges were actually classified as critical bridges, which required them to remain elastic under level 1 earthquake and with limited damage under level 2 earthquake. The seismic performance is actually same as that of the Japanese standard, which measure performance in terms of 3 criteria: the seismic safety design, the seismic serviceability design, as well as the seismic repairability design. This slide shows you the articulation on the behavior of isolators under level 1 and level 2 earthquake. The concept is at level 1 earthquake, the isolator is expected to remain elastic, but it will move in the longitudinal direction, but it is fixed in the transverse direction. The fixity of the system at the transverse direction is provided by what we call shear keys to prevent the system from moving in the said direction. At level 2 earthquake, however, the isolators are now allowed to move in both direction, longitudinal and transverse direction. Showing you here the articulation under level 1 and level 2 earthquake, including the specific seismic performance objective and how we have implemented this system, including the modeling on shear keys. Of course, wind demand was ensured to be less than the yield capacity of the isolation system. This slide shows the details of the isolator used for Panshan Viaduct projects. The isolators are rectangular, 610 by 610 at expansion and abutment, and 640 square at continuous supports. The isolators are to be placed at the construction of cap beams with sleeves provided before the installation of the girder. Other parameters of the isolators are provided here, such as the hysteresis, the modeling, as well as the maximum displacements. This slide here shows the performance of the 2 model bridges. We modeled both a bridge Panshan model non-isolated and a similar bridge but with isolated system. You can see here the slide shows the results of the model analysis comparing the non-isolated versus the isolated case. It is evident from this comparison that there is a period shift, which is approximately 2 times the period of a non-isolated bridge system. This slide shows the comparison of the seismic shear demands between the non-isolated and the isolated bridge models, which clearly demonstrates the effectiveness of seismic isolation. For the non-isolated bridge, the seismic forces are transferred more directly into the substructure, resulting in higher shear demands at the piers as well as in the foundation. With seismic isolation, however, the flexibility and energy dissipation capacity of the isolation system reduce the transmission of seismic forces to the bridge substructure. And as a result, the isolated bridge shows significantly lower shear demands compared to the non-isolated bridge. This slide here shows the critical pier that was selected in order to compare the displacement time history response of a non-isolated bridge model and the isolated bridge model. For the non-isolated bridge, the pier directly participates in the resisting of seismic demand, and as a result, larger displacement and response were observed, indicating some significant deformation demand in the substructure. In contrast, if you look at this graph, the isolated bridge shows a substantial reduction in the pier displacement. And this is because the isolation system lengthens the period of the bridge and concentrates much of the seismic movement on the isolation level only, rather than transferring it directly to the piers. Now, this reduced displacement demand at the critical pier demonstrates the effectiveness of isolation in protecting the substructure. To check the performance of the substructure, these two slides here presents the two pushover curves for the critical pier showed earlier, both in longitudinal and transverse direction. The curves are compared with displacement demands obtained from the nonlinear response analysis for level 1 and level 2 earthquake cases, considering both non-isolated case bridge and isolated bridge models. We can see here, as we can see in this slide, that for the case of the non-isolated bridges, the level 2 displacement demand exceeds the yield displacement of the critical pier. This indicates that the pier is expected to experience some inelastic deformation and possible damage under level 2 earthquake. In contrast, the isolated bridge model, the displacement demand remained within the elastic range of the pier even under level 2 earthquake. So this means that no significant damage is expected from the substructures because of the effectiveness of seismic isolation. So this comparison clearly highlights the effectiveness of seismic isolation in reducing the demand to the substructure by shifting main seismic deformation to the isolation system, allowing the bridge to remain elastic even during strong earthquakes such as level 2 ground motion in this study. Thus, it contributes to the resilience of this structure during earthquake. Now, aside from this case study that we have presented, there are still other multiple bridges that have utilized seismic isolation, which has started to gaining popularity here in the Philippines. For example, the Clarin Bridge in Bohol is also installed with seismic isolation system, also from Japan, and has been installed with devices like dampers. Other ongoing projects that utilize the seismic isolation system for bridges are the following. One is the Bataan-Cavite Interlink Bridge Project by T.Y. Lim, and the other is the Amburayan Bridge 2 project, also by Petrojican. Now, these examples now highlight the broader application of seismic isolation system in the Philippine bridge engineering practice. As a concluding remarks, we can say that the bridge seismic design practice in the Philippines has evolved far from the conventional Spanish colonial era stone masonry bridges, force-based design approaches to the current performance-based framework that we have been adopting locally in the Philippines. Nowadays, the functionality of the bridge after a major earthquake is becoming a sought-after post-earthquake strategy for most of our bridges. And seismic isolation system, when applicable, is considered a promising solution to address the functionality and predictability behavior of bridges. Thank you for listening.
Thank you very much, Dr. Rodolfo. That was very great presentation. And finally, we have Professor Tomonori Nagayama Sensei. So it's all yours now.
Thank you. Let me share my screen. Okay. Okay, do you see my slide?
Yes.
Okay. Okay, good evening to participants from Asia, Philippines, Japan, Asian countries, and good morning, good afternoon for other participants. I'm Tomonori Nagayama from the University of Tokyo and also Vice President of IABSE. And it's my great pleasure to give this presentation at this IABSE webinar. My presentation title is as written here, Monitoring Informed Seismic Response Assessment and Control of Bridges in Japan. The main message of my talk is that Japan has developed many seismic technologies for bridges, such as seismic resistant devices, isolation control, and fail-safe devices. However, to understand whether these systems really perform as intended, monitoring is essential. So Japan is highly earthquake prone, and large earthquakes have repeatedly caused serious damages to bridges and other infrastructure. 1995 Kobe earthquake was a major turning point for seismic design and retrofit in Japan. And I was a high school student at the time. And the structural collapse and many casualties were very shocking to me. So this experience was one of the reasons why I became interested in civil engineering. Actually, this is common to many of my classmates was civil engineers in the same age. Since then, seismic design and retrofit technologies have significantly improved, and newer structures and properly retrofitted structures generally perform well under earthquakes. On the other hand, older structures and non-retrofitted structures can still remain vulnerable, and even new ones may not perform as intended, as in this case, damper broke during Kumamoto earthquake 2016. First, I would like to briefly review the main categories of bridge seismic technologies in Japan. The first is seismic resistant design. In this approach, the structure resists earthquake force mainly by strength and ductility, and damage may be allowed in designated components under severe earthquakes, but collapse should be prevented. A typical example is the steel jacketing of RC bridge pier, and this improves strength and ductility of existing reinforced concrete piers. The second is seismic isolation. Flexible bearing lengthen the structural period and reduce the transmission of earthquake fault. Additional damping can also reduce the displacement and energy demand. And the third is seismic control. Dampers or control devices reduce seismic response by dissipating energy or applying control forces. And in Japanese bridges, these concepts are often combined with lateral force distribution systems and other fail-safe measurement, fail-safe measures on the next slide. The first one is unseating prevention. This prevents the girder from losing support and falling during a major earthquake. This is directly related to collapse prevention. The second is vertical step prevention. Even if bearings are damaged, large roadway level differences should be avoided, especially for emergency transportation routes. So this measure is related to post-earthquake trafficability. The third is the lateral displacement restrainer. This restrains transverse movement of the superstructure and improves transverse stability. These systems are not always very visible, but they are very important for bridge resilience after major earthquakes. Here, this is one example of seismic resistant design for retrofit of BPA bearing plate type A bearing on the Metropolitan Expressway. BPA bearings suffered damage during past earthquakes, and they were originally designed for level 1 earthquake, small to moderate earthquake, and partial bearing fall-off was observed. Replacing all of these bearing is costly and time-consuming, so efficient and effective retrofit method was developed by Tokyo Metropolitan Expressway. The retrofit uses reinforcement blocks, steel rods, existing bearing, and high-strength boards. The basic idea is to improve the bearing capacity without replacing the existing bearings. This slide shows the effect of the retrofit. After retrofit, the bearing capacity becomes much higher. The target level is increased from the level 1 small to medium earthquake demand to much higher level 2 demand. And another important advantage is short installation time. The method does not require jacking up the girder and removing the existing bearing or adjusting the reaction force. The installation procedure is very simple. Remove the existing side blocks, install retrofitting members, and tighten the steel rods. So this is a good example of practical seismic retrofit for existing urban expressway bridges. And next, I will show an example of seismic control using a transverse displacement friction damper. In metropolitan areas, damage to the pier base should be avoided. This is because space around the pier base is often very limited, and damage assessment and repair are difficult for underground or congested components. So the concept here is to use bearing or devices that remain fixed under small to medium earthquake, level 1, but allow movement under large earthquakes. So under level 1 earthquake, the device works as a restraining device. Under level 2 earthquake, large earthquake, it allows displacement and works as a damper. This slide explains the mechanism more clearly. Under level 1 earthquake, on the left, the small to moderate earthquake, the device prevents lateral movement of the girder. This helps protect expansion joint and maintain normal serviceability. Under level 2 earthquakes, large earthquakes, on the right-hand side, the device works as a fuse and damper mechanism. It releases the movement of the superstructure, caps the inertial force demand, and provides seismic damping. As a result, damage at the pier base can be significantly reduced. This is an important idea. Instead of forcing the pier base to resist all seismic demand, we allow controlled movement of the replaceable or accessible devices. This slide shows an application of the friction damper to an actual urban viaduct. Because of severe spacing constraint. The structural configuration is quite complex, and retrofitting the pier base is difficult. However, damage to the pier base should be avoided. So transverse friction damper. Transverse friction damper is effective solution for this case because it controls seismic response at an accessible location and reduces the demand on the pier base. You can see the installed damper in this photo. Now, I would like to introduce the concept of functionally separated bearing systems. Conventional isolation bearings often concentrate many functions in one component. For example, they support vertical load, resist horizontal load, dissipate energy, accommodate displacement, and provide restoring forces. So this is efficient if we single one bearing have all functionalities, but it also creates a problem. If the bearing is damaged, many functions may be lost at the same time. Also, in some cases, designing bearings satisfying all functionalities at the same time becomes infeasible. For example, rubber bearing dissipating energy for the horizontal motion cannot support very large vertical load. In a functionally separated system, these functions are distributed among dedicated components. Vertical load support, horizontal force resistance, fail-safe functions are separated. So the advantage is that damage can be guided to replaceable damping devices, while critical bearing failure is avoided. This enables more rapid recovery after extreme earthquakes. This concept is further extended here as a functionally separated bridge system. The key idea is damage location control. Some components are difficult to inspect and repair, while others are easier to replace. And therefore, we intentionally guide damage to components that are accessible and replaceable. One example is the cylinder and steel series damper, or CAS. It consists of a steel damper, and a cylinder type damper connected in series. The cylinder damper accommodates slow movement, such as thermal deformation. This helps avoid unnecessary fatigue damage to the steel damper. During strong earthquake, level 2 earthquake, the velocity-dependent cylinder damper becomes relatively stiff, and the steel damper yields this part yields and dissipates seismic energy. Therefore, the system can accommodate daily movement, dissipate earthquake energy, and concentrate damage in replaceable component. When we look at the bridge as a whole, piers in the river are difficult to repair, while the bearing at the abutment have easy access and easy to repair. Therefore, it's better to design energy dissipation functionality at the abutment bearings. So cylinder and steel series damper is thus installed at the abutment. In short, the message is separate functions, control damage, and recover quickly. So far, I have discussed design concept and devices. However, very important question still remains. Do these systems really perform as intended during earthquake? This slide shows a famous example. Onneto Bridge, a base isolated bridge investigated by Choudhury, Abe, and Fujino. As many as you know, Professor Yoza Fujino sadly passed away on June 6th this year, and I'd like to take this opportunity to express my sincere respect and gratitude for his tremendous contribution to our field. Here in this monitoring data, revealed a typical seismic response. The girder and pier cap moved almost together. Two lines are very close with each other with negligible relative displacement. This means that at the instrumented piers, the isolation bearings did not allow the intended relative displacement. The likely reason was that side stopper obstructed the movement of the isolation bearing. This example clearly shows the importance of monitoring. Without measured seismic response data, such a hidden malfunction would have been very difficult to identify. Monitoring helps close the gap between design assumption and actual structural behavior. There are other examples showing the real performance of seismic device after a major earthquake. In the example on the left, a rubber bearing fractured during the 2011 Tohoku earthquake, although they were expected to dissipate seismic energy without fracture. In contrast, the bridge on the right shows that rubber bearing can work as intended. The relative motion between the girder and the pier is clearly observed. Therefore, it is important to validate design assumption under real earthquake conditions. Field inspections after earthquake remain essential, but monitoring data and camera recordings can provide direct evidence of the actual seismic behavior of bridges. This slide shows seismic response monitoring after the 2016 Kumamoto earthquake. We installed wireless sensors on a bridge and recorded aftershocks for about 2 weeks. During this period, about 60 earthquakes were observed. The bottom figure shows an example of recorded acceleration. Although the sensors were battery-operated IoT nodes, the data quality was high. P-wave and S-wave arrivals can be clearly identified, and the sensor nodes were well synchronized. So this kind of monitoring allows us to observe bridge response under real earthquake excitation. In other words, an earthquake can be regarded as a full-scale experiment on the bridge. From the monitored seismic responses, we can estimate not only global response, but also structural properties of components. Here, relative displacement response of rubber bearings were obtained from acceleration measurement. Using these responses, the stiffness of rubber bearings were estimated. The estimated stiffness differed from factory test results by only about 10%. This is important because rubber bearings may degrade relatively quickly compared with many other bearing components. Monitoring allows us to evaluate the structural properties under actual service conditions. Bridge monitoring under real earthquake is becoming increasingly important. In Japan, National Institute for Land and Infrastructure Management under the Ministry of Land, Infrastructure, Transport, and Tourism has installed strong motion monitoring system on 25 road bridges of various structural types. This slide may be a bit late, so now we may have more bridges instrumented with this system. Anyway, the data help validate seismic design assumption. Now, I will show an example from Yokohama Bay Bridge. Yokohama Bay Bridge is a long-span cable-stayed bridge and is an important transportation link. Understanding its seismic behavior is therefore very important. During the 2011 Tohoku earthquake, transverse pounding was observed between the wind tongue and wind shear, which are important seismic response control device for long-span bridges. This wind shear and wind tongue restrain the motion at the tower link. The lateral displacement, lateral direction acceleration recorded shows periodic impulsive responses. So these spikes indicate pounding. This phenomenon was not recognized before the earthquake and was not considered in the design. The observed pounding may have serious consequences. If the wind tongue or wind shear is damaged, the damage can propagate to other components such as tower link, cables, and girders. Actually, minor damage was observed at the tower link at the 2011 earthquake. In the design, the wind tongue and wind shear were assumed to move together without pounding. However, the monitoring data showed that pounding occurred in a transverse direction, which is different from design assumption, and this phenomena is further studied. This is lateral direction acceleration records during the earthquake. We estimated natural frequency during this 600-second earthquake response. Then we observed that the frequency increased at the beginning and then decreased. If the bridge is linear, the natural frequency should remain constant. If we consider nonlinearity, usually frequency should decrease at the beginning during large motion and then increase. But here the frequency actually increased. This is very much different from the design assumption and our understanding. We then included small gap, 5 millimeter gap between wind shear and wind tongue in the model. Then we were able to reproduce the frequency change. With this model, the acceleration time history and the frequency spectrum are very well reproduced. Yes, time history shows good agreement. Then with the 5 millimeter gap, detailed FEM around the wind shear and wind tongue are prepared with a shell element, and a multi-scale model was constructed. This model allows us to evaluate local deformation and possible damage model under seismic excitation. Using this model, consistent with the observation, a level 2 design earthquake was applied. The analysis showed that the base part of the wind tongue yielded, and the gap increased due to pounding. This indicates that the repeated pounding can cause local plastic deformation and damage. The key point is that the monitoring data helped us identify the real mechanism, and the validated model helped us evaluate possible damage under extreme events. This slide shows a more critical consequence. After damage of the wind tongue, the tower link may experience large displacement. In the analysis, the pin of the tower link can come out from the link brackets, which means the drop-off of the tower link can occur. The important message is that the detailed FEM, consistent with seismic event observation and monitoring data, clarify the seismic performance under extreme events. So far, we have discussed monitoring for understanding real behavior and validating models. The next step is post-earthquake rapid assessment. Rapid assessment is essential after earthquakes. For moderate earthquake, it helps reduce downtime and economic loss. For severe earthquakes, it supports emergency response. For structural damage, displacement is a key indicator. For example, industry drift in buildings or relative displacement in bridge component is closely related to damage. However, displacement estimation from acceleration is difficult, especially in the nonlinear range. So double integration may work in the linear range with appropriate filtering, but nonlinear and residual displacement estimation remains challenging. To address this problem, we have studied deep learning-based displacement estimation. Here we use dilated CNN. The advantage of dilated convolution is that it can have a wide temporal receptive field. It can efficiently capture long-range temporal information without using an excessive deep network. The input is ground acceleration and absolute acceleration responses, and the output is relative displacement response. The model is trained using diverse nonlinear single degree of freedom system with different hysteresis models. The aim is to estimate nonlinear and residual displacement from acceleration records. The trained model was validated using nonlinear Abacus FEM model. Two structures with different damping ratio, natural period, and historic behavior were considered. The result shows that the nonlinear displacement response can be estimated from acceleration responses, even for FEM models that were different from the training single degree of freedom models. So this suggests the potential of data-driven displacement estimation for rapid post-earthquake assessment. We are now extending displacement estimation from a single pier to a bridge system. A detailed forward simulation model with soil path was used for simulation to generate response data, while reduced order model without soil path was used for Kalman filter-based displacement estimation. Despite model simplification, it's simplified, displacement was estimated accurately, 1 to 10% error laterally and less than 2.5% longitudinally. This shows the potential of acceleration-based displacement estimation for bridge-level post-earthquake assessment. To conclude, I'd like to emphasize three messages. Japan has developed diverse seismic technologies for bridges, from resistance and seismic resistance, isolation control, fail-safe, and trafficability measures. Monitoring informed assessment is essential because real bridge behavior may differ from design assumptions. Monitoring helps identify hidden mechanisms and validate seismic performance. Finally, acceleration-based parameter and displacement estimation can support rapid post-earthquake assessment. The next step is application to more complex bridge and nonlinear damage scenarios. So before concluding, I'd like to acknowledge the support I received in preparing this presentation. I'm grateful to Metropolitan Expressway Company Limited for providing materials on seismic retrofit response control technologies, and to Professor Ji Dan of Saitama University for material on functionally separated bridge system and cast damper, and Dr. Yosuke Ishii from MLIT for materials on strong motion monitoring system for bridge in Japan, and to the member of my laboratory for their contribution to the monitoring, modeling, and the displacement estimation studies. Thank you very much for your attention. This is my presentation.
Thank you very much. Okay, so give us another 10 or 15 minutes. All the speakers, can you turn on the cameras, please? So let's move on to the questions and answers sessions now. So, Professor Takeuchi, you already answered the questions in the Q&A, but can we explain to the audience since they
Okay,
cannot read it
okay,
here? So maybe you can
so
choose 2 questions.
yeah, three questions. So can you hear me?
Yes.
Okay, so first question, how proportion of the isolation and the response control decide? That is probably talking about the combined system. So actually that it depends on the building. So aspect ratio proportion of the buildings, but I think it's the project by project. In many cases, the optimization design process to parametric study and the automatic optimization process is for combining seismic isolation and response control is often employed recently. Can we answer the? That is answer for this question. The second
Okay.
question, can we store the energy absorbed by dissipators in battery? That is a good idea, but I'd like to say the earthquake is actually rare and it is not worth for the investment, I think. So if we have energy absorbing against the wind vibration, it continuously works, it might be worth considering. So that is answer. And the final third answer, the question that Japan has adopted the performance-based seismic design for decade. How do owners specify acceptable post-earthquake functionality, and how does that influence the choice of isolation or damping systems? So that's also the nice question. Recently, of course, the seismic isolation or response control might be a little bit more expensive than ordinary seismic the design the options, but the recent earthquake experience have led to more property owners to become conscious about business continuity after earthquake and probable maximum loss that the PML was. So more understanding for the owners for the worth of the seismic isolation or the response controlled. Also, this month, the Japan Structural Consultant Associates, JASCA, launched the third-party seismic ratings certification service, rating from platinum to gold and silver and the bronze. It's 4 grades about the required design code, similar as a Redis rating system in west coast of the US. So probably the more services for the higher the performance-based design can be to have a popularity for the building owners. I hope. Yeah, that's my question, but that's my answer.
Thank you so much. So audience, if you have another questions, you can send us email or something. All right, so Dr. Rodolfo, you have 2 questions. Can you answer like quickly? Like, can horizontal damper use with the isolation in the bridges, and can we provide damper between the seismic arrestor and a girder?
Yes, this is a very common combination also for bridges. We can design both isolator as well as damper, depending, of course, on the target performance of the structure as well as the target configuration. If, for example, the lead in the lead rubber bearing is not sufficient, then a damper can also be added to support it.
Okay, so
And
did you sorry. So can we provide the damper between the seismic arrestor and the girder?
Yes, I think the question is
Okay,
almost similar.
okay.
Yes. For number
Great.
3,
How
how
much
much additional construction costs is associated with the seismic isolation in bridge construction? Is this justified, resulting reduction in seismic demand and structural damage? And how we can convince the client to use seismic isolator? I think related to the response of Takeuchi Sensei, I think initial investment with isolation is very high in comparison with the conventional approach, but if you look at the overall life of the bridge, particularly the post-earthquake response, repair, and the restoration after a major earthquake, overall it might actually compensate for that initial investment cost using seismic isolator. I think for the case of buildings, the JSSI in their manual provided a comparison of the cost of an isolated building and non-isolated building. And initial cost is really high for the isolated building, but overall life cycle of the structure shows that seismically isolated structures have lesser costs overall. Thank you.
Okay, thank you so much. So finally, Professor Nakayama, you have these big questions. How do you balance the design?
I think the very last question is for
Yeah.
buildings. Maybe first I append my answer to the previous one about the cost. So no, I agree with the previous answer, but by introducing seismic isolation or other devices like cost for piers or piles, those costs can be reduced. So overall, in many cases, it's more cost effective to install seismic isolation system or other seismic control devices. And also, in some cases, in urban environment, there is no option, no space for other option, no space to retrofit to employ seismic resistant design and so on. So seismic isolation or installing some seismic control device is the only option in some cases. And the last one, yes, this is especially for high-rise building in Japan.
Yeah,
so
I can explain that for the of course the seismic isolation makes the system in the software, but we have usually to have two level of the stiffness, and the for the wind forces are usually to designed with the high stiffness with like a steel or lead damper have giving a high stiffness for the elastic ranges, and for the that is still in elastic, kept in elastic in the wind forces. And after the introducing a big earthquake, then they yield and elongate the natural period and getting softer. So for the building with a high, bigger the facing area, and but it's lightweight cases, wind forces sometimes governed than the seismic forces. In that case, that kind of the locking system of the viscoelastic damper is employed. It's like locked for the wind forces, and for the seismic forces, it's unlocked and then to start moving around. That kind of system also in the practice. Can we understand? Can you answer your answers?
I think so. The technology is like improving very well, like day by day. So, do you have any questions from Professor Nakamura or Dr. Andres, or comments or something from the moderators?
Yes, not an moderator, but an audience. I'd like to ask a question to Rodolfo. Yes, it's not a technical matter. Well, it's not directly related to your speak, but we heard that the news that a strong earthquake hit recently the Mindanao Island. I hope your family and friends are all safe and well. Just tell me that did your buildings or bridges suffer any serious damages or any casualties, many casualties, something like that? Can you
Thank
give
you,
some
Sensei.
information about that? Yes.
Yeah, thank you, Sensei, for the concern. Yes, we had this earthquake in southern Philippines, and our group, the Association for Structural Engineers of the Philippines, responded to this earthquake as part of our mandate to do post-earthquake reconnaissance. And actually, the observed damage to these structures is not relatively, it's not totally massive, and most of the damage are with the same damage that we observed from past earthquakes, which are mainly on non-engineered building systems. In particular, we are now increasingly taking into consideration the common damage to non-structural system, which in most cases is the cause of fatalities recorded in this type of earthquake. There is no current guideline on how to address non-structural system in the Philippines, and we are currently looking at improving and looking into this matter on how we can address the design of these non-structural components.
Thank you very much for your information.
All right, I think this is a good time to close this webinar. So including us, like Japan and Philippines, many countries are still suffering for the earthquake. I hope many countries can protect the damage from the earthquake, like using these beautiful technologies, provided the Yabse engineering organizations. So before we close the seminar, please join me in thanking all the wonderful speakers, and once again for their beautiful presentation. Thank you so much for the preparation and everything for you. Thank you so much. Also, we really thanks for the Professor Nakamura and Professor Andres to introduce the national groups, and all the Japanese and Filipinos welcome to join us anytime. And also, of course, like we really appreciate that you enjoy these 2 hours long webinars today. So like really thank you so much for joining us today. And thanks again like for the sponsors too. I really appreciate the sponsors for 2 companies. All right, so have a great night for the Asians, like it's like 11 o'clock. And have a great afternoon for the Europeans, and have a great day for the people in the United States or somewhere. Thank you so much again for everybody, and see you very soon.
Thank you very
Okay.
much.